Good morning. Today, Roberto and I will talk about our lessons learned about a new typology, passive house commercial kitchens. Our presentation is based on two Canadian projects for the University of Victoria and the University of Toronto, which are both leading the way with the delivery of passive house institutional buildings with large commercial kitchens. In terms of content, we'll start with the challenges faced with this new typology. We'll then run through the three areas which have the largest impact on the kitchen's energy consumptions. And we'll then conclude with a design guidance summary to be used as a starting point for any teams out there designing other commercial kitchens. Okay, so where are we starting from? Mixed-use buildings made of residential areas above a non-residential podium are now a common typology. However, in our case, this podium houses a commercial kitchen delivering several thousand meals a day, ranging anywhere from 2,000 to 9,000 meals per day with the university projects that we're talking about. And we are trying to fit this all into a passive house building. So, what are the challenges that we're facing? First, due to the cooking requirements that we have in the kitchen, there's a need for large exhaust flow rates, shown in pink in the diagram. Then, this exhaust flow rate has to be balanced with makeup air to maintain the building pressure, shown in blue. However, looking at the winter case, this cold makeup air has to be preheated to adequate temperature to avoid occupant discomfort, and this is where a significant portion of the kitchen's energy consumption goes. And then the other challenge faced comes directly from the kitchen equipment energy consumption, which is fairly energy intensive. So to approach these challenges successfully, the first thing we had to do was to start with defining clear targets.
We needed to set targets in terms of space heating demand and primary energy. So we have to consider that commercial kitchens are typically in mixed-use buildings, so we may have more than one PHPP. Space heating demand limit remains 15 kWh per square meter per year, calculated with an area-weighted average between all PHPPs. And the factor that impacts the most the space heating demand is the kitchen ventilation. For the primary energy, we need, for fair metric, the PR limit is set as 60 kWh per square meter per year, plus an additional per meal allowance. And we have to include electricity and domestic hot water consumption for all the other kitchen equipment. Kitchen ventilation system has a huge influence in the energy demand of commercial kitchens. And to get a better understanding of which are the numbers we are talking about, the final UVIC model has an average airflow of 17,000 cubic meter per hour, which are close to 10 air change per hour. So the main question is, how much air do we need? We can say that the main target is the reduction of the kitchen exhaust to a minimum, because the main problem is the price in energy terms for preheating the makeup air to balance exhaust requirements. We can start with an improved kitchen planning, taking into account the following point. Use of equipment with less heat production, so induction cooktops, grouping appliances with similar cooking schedules. In UVIC, the stations have been reduced from 10 to 7. And putting high exhaust station at the center of exhaust. The arrangement of the extra wood in the room has a big influence on the ventilation efficiency, and so on the required extra air demand. For example, the extra air demand of an extra wood, which is positioned with one long side next to the wall, reduced up to 37% the extra air demand compared to free positioning in the room. Another two geometrical parameters which influence the extra air demand are the hood overhang in relation to the depth and the width of the cooktop, and the distance between the lower edge of the hood and the top of the cooktop, which you can see the dimension in red with the letter Z. And reducing the distance from 1.6 to 1.2 meters, the extract air demand is already decreased by 22%. Use high capture efficiency hoods. In this system, we have cold supply air blown directly into the hood. The effect caused by this flow improves extract air capture, reducing the needs of extract high airflow. In all the normal range hood, we can determine a suction area which has the same measure of the extract duct. Within this area, we have 100% of the efficacy. Everything outside this area is not caught by the exhaust duct, unless increasing the volume flow. In a high capture hood, all the fumes are pushed into the suction area by the cold air coming from the range hood itself, reducing in this way the airflow needed in the exhaust duct. This is why this technology is so useful to reduce the ventilation system heating energy demand.
After incorporating all the planning approaches that we've just seen, the next strategy is to incorporate demand control ventilation, which means to ventilate as needed rather than overventilating. So how is this done? This is done through the use of sensors to regulate the kitchen exhaust requirements. And these systems can have different levels of sophistication. The more sophisticated ones, like the ones we're using on these university projects, they have exhaust temperature sensors, room temperature sensors, as well as infrared sensors to detect the cooking status of the kitchen equipment and adjust the flow rates accordingly. So this is a great kitchen feature for energy efficiency, but it is difficult to predict the exhaust flow rate profile over a typical day. Does this demand control ventilation have a large impact on the kitchen's energy consumption? At the very beginning of the project, we didn't know. So we did a PHPP sensitivity analysis, varying, as you can see on the graph, the average exhaust flow rate from 30 to 50% of its maximum. And that led to a change in the space heating demand of the podium space from 25 to 40 kilowatt hour per square meter per year, i.e. a very large impact on the non-residential portion of a model. So we realized that we needed a deeper understanding for that key variable. And with the absence of data, we actually went to the University of Ottawa to get some monitored data. We took exhaust flow rates measurements at 5-minute intervals over a typical week for the kitchen system that they have, which is similar than the one specified on our institutional kitchens. And what we found for the graph on the right is the blue portion of the graph is the monitored profile, and the orange was the maximum exhaust flow rate that the system was designed to meet. And this graph shows that having a demand control ventilation system like this one led to a reduction of the average exhaust flow rate from 100% to 65%, so about a 35% reduction. After incorporating the planning considerations and the demand control ventilation, the third strategy that we implemented on our design was the cascade ventilation approach. We already know that the preheating of the makeup air is actually a costly requirement in terms of energy consumption. So this way, we can actually maintain the same level of exhaust requirement, but we are reducing the makeup air by supplying fresh air in an adjacent place and cascading it to the kitchen. Finally, the fourth strategy implemented into the design is the use of a ventilation system with heat recovery. Using a heat recovery on kitchen ventilation is tough on several technical aspects, as Roberto will explain in the next slide. And our journey on the procurement side was also particularly difficult. As you can see from the slide, we started with the original Halton heat recovery unit, which actually was discontinued halfway through the project. So we started investigating a bespoke heat recovery unit, which didn't quite make it through. So we turned around to look at the units that are available in Europe. That was a good start, but we discovered there are mainly too small, and most of the time not having the correct North American standard approvals. So we also couldn't proceed on that basis. Trying to find that benefit that the heat recovery was bringing, we took a little detour investigating earth tubes before finally settling on a combination of the Halton polystop unit, which is a pollution control system, combined with a runaround coil, which is the system bringing us that heat recovery feature.
Like every passive house, the heat recovery ventilation system is a must, but here we should take some precaution due to the particular ambient. The grease contained in the extract air constitute a general problem for heat recovery system in kitchens. It can lead to fire loads in the duct, issue of hygiene, or clogging of the heat transferring surfaces. So effective separation of the aerosols from the extract air is necessary, absolutely necessary. Then, linked to this previous point, we need an easy access to all the components for cleaning and inspections. And for operation in summer, kitchen ventilation system with heat recovery must always be equipped with a bypass. Then all these points we have seen so far have been used within UVIC project, and they have helped a lot to reduce the ventilation heat losses. So use of equipment with less heat production and grouping appliances with similar cooking schedule. So no more island station and high capture efficiency hood has been used. Then demand control ventilation system to get a tailored airflow rate in terms of time and power. Use of kitchen supply air providing from adjacent places to save energy on preheating the supply air. And last but not least, use of heat recovery.
As Roberto summarized, these 4 strategies were implemented on the university projects we worked on. And this graph in front of you displays their cumulative impact on the space heating demand for the podium of the University of Victoria project. And what we can see is that there is a clear need to combine all strategies to reduce the impact of the kitchen ventilation on the building's energy demand. Without that, there wouldn't have been a way to bring the, space heating demand of the podium back in line with the passive house levels of performance we were aiming at. After having focused on the kitchen ventilation, which has the largest impact on the kitchen's energy consumption, we'll move on to culprit number 2 and focus on the kitchen equipment itself. So where are we starting from? As Roberto mentioned earlier at the start of the presentation, we are now using a kilowatt hour per meal metric to have a fair metric based on the number of meals delivered rather than the size of a kitchen. And with that kilowatt hour per meal metric, there is not a lot of benchmarking data out there. The little bit we've been able to find has been with the CIPC TM guides, and they were stating, that the price tag in terms of energy per meal varies between the 4 to 5, depending on, best practice to typical practice. And this is where we're starting from. After quite a lot of discussion with PHI, the additional final energy allowance that we got given was 1 kilowatt hour per hot meal and 0.25 kilowatt hour per cold meal. So you can see the kind of differences. And you have to more or less take the average of the two, which will be project specific and depending on the hot and cold meal split that you're going to see on each project. So, for instance, on both university projects, we've seen that average kilowatt hour per meal vary along the line of 0.65 to 0.85 kilowatt hour per meal. So, again, that gives you a kind of, context for the type of energy consumption reduction we're aiming to achieve. So, How did we meet these targets? Roberto will now dive in and explain the design strategy that were chosen around the kitchen equipment specification.
We can say that the kitchen equipment calculation follows two approaches. The first one is the quantitative approach, which gives us the number of our energy consumption. This first point seems enough to get to the correct numbers, but sadly, there are not enough monitoring data or data from the manufacturers, like we have for residential appliances. So, to evaluate precisely all values, a qualitative approach help us to choose the right items, being a sort of guideline for choosing the most efficient appliances. And for instance, we should not use open coolers, so coolers with doors or glazed doors, and highly insulated coolers with at least 5 inches of insulation. And usually the normal industry insulation is around 3 inches of thickness. Then walk-in coolers or freezer with insulation on 6 surfaces and recessed floor slab to accommodate walk-in insulation. And this is the details you can see from the UVic project. Then a double set of airtight and insulated doors, insulated traffic doors during operation and insulated sliding doors during off time. Then induction kitchen technology and use efficient equipment with the double or triple glazing and so on. For instance, oven is an example of how one of the highest energy intense appliances can reduce its energy demand. For instance, we can use electricity instead of gas, using better insulated device casing, triple glazing with low emissivity coating, using condensation hood externally, which brings up to a 75% of reduction in exhaust requirements compared to combi steamer without recirculation hood, and a demand control hood only used when steamer door is open. Here, a detail of conventional steamer with steam generator. We can see the hot condensate is drained away unused into the wastewater pipe, and the fresh water supply is made by cold water. But a further efficiency potential is offered by utilization of the heat contained in the condensate.
While we were following this qualitative approach to ensure that all best practice strategies were implemented in our design, we also pursued a quantitative approach through detailed calculations. And this was done to assess the electricity consumption literally element by element. The calculations are done for each piece of equipment, and to do so, we needed to understand the kitchen equipment usage profile to predict their electricity consumption accurately. And this is where a lot of input from both the kitchen consultant and the kitchen staff was needed. You can see a snapshot on the top part of the screen. Having completed that first step, the next step was to focus on the 20 pieces of equipment with the largest electricity consumption to refine our calculation. We started looking at these pieces of equipment and understanding their use with a little bit more granularity. For instance, to understand the difference in power consumption between warm up and keep warm modes, as well as how long would they be in these respective modes. And here I share the journey that we took through the UVic kitchen equipment calculations. So you can see that we went through a few ups and downs before delivering a design that was finally in line with the PHI requirements that we were given for this project. And so where are these ups and downs coming from? So first of all, the design process took us quite a while. So throughout the design process, we received kind of updated data. We've also seen kind of new and more efficient products arriving onto the market where we were able to switch for better performing equipment as we went along. We also, after some research, managed to switch some of the remaining gas-fired equipment to electricity-based equipment. And what we also found through that process is that there has been a lot of refinement through deeper understanding. And that deeper understanding around how everything was working allowed us to kind of highlight some inefficiencies that we weren't aware were part of the design. And we were then able to rectify them to get us all the way down to the performance levels that we were after. And this would not have been possible without a really deep involvement from every single design consultant at the table, including the client staff. Finally, for the last piece of the puzzle, we'll review the kitchen's domestic hot water consumption. So for context, we have a building housing 400 students, a central laundry room, and the commercial kitchen. So when I started doing the calculations, I initially thought that the domestic hot water demand for the residential portion would actually be the largest. And as you can see from the graph, I was pretty wrong. The kitchen is by far the largest domestic hot water demand for that building. So what are the strategies that we used to reduce that domestic hot water consumption? Of course, the first step is always to reduce. So looking at using cold water wherever possible and low flow features. Something fairly straightforward before moving on to step 2, which is recovering and using that waste heat if available before step 3, trying to electrify. So in terms of the key design improvements, they are really around that use of waste heat that is available to preheat domestic hot water wherever possible. So to start with, of course, at a local level, this is mainly seen through the dishwashers, but every single dishwasher that we have throughout the kitchen is actually equipped with a wastewater heat recovery feature. So we are first and foremost recovering from a local level. Before zooming out and looking at the kitchen as a whole and trying to do waste heat recovery at a more central level. So what are we talking about? We have high temperature waste heat available from the refrigeration system because we do have quite a lot of large walk-in freezers and coolers, right? And all of these are going to generate waste heat. And by having all refrigeration equipment connected to one central compressor system, this allows us to use that waste heat towards domestic hot water preheating, which can contribute to quite a big offset on the domestic hot water demand. So really, good feature if we can implement that into the kitchen. And so with that approach, of course, we looked at it from a calculation standpoint, similarly to the electricity kitchen equipment consumption. So we also went through an element by element calculation to understand the kitchen energy consumption as it relates to domestic hot water. And the calculations look at the domestic hot water demand, of course, in addition to the temperature set points, which we saw could vary widely to the lowest around like 43 degrees Celsius all the way to 100 degrees Celsius, as well as the energy sources, because we do have different energy sources from, heat pumps, start electric, as well as, the use of heat recovery to produce domestic hot water in this kitchen. And all of this bundled together helped us pin down a kilowatt hour per meal figure as it relates to domestic hot water consumption.
Design guidance. In this next chapter, we are going through the main points we have to keep in mind and their energy saving potential. In general, the ventilation system should be adapted to the kitchen usage and work processes. Starting from a typical energy consumption for each meal, we can see that the energy demand based on a kitchen ventilation system without heat recovery could be reduced up to 85% using the following measures. Kitchen appliances with reduced load, accurate kitchen planning, kitchen hood design, so use of ventilation guards. Keep in mind the height between cooking surface and hood. Demand control ventilation, so dimensioning of extract air quantities according to the actual equipment configuration and kitchen use. Sensor and induction technology, and heat recovery from exhaust air. Use of heat recovery from extract air from preheating supply air. The energy consumption related to the kitchen equipment is related to a large number of appliances, which are used for the various processes of food preparation. These factors have a major influence on energy efficiency. Using electrical devices instead of gas. Thermal quality of appliances using improved casing insulation with triple glazing with heat reflective coating. Eco mode or standby function help to reduce the standby losses, and enclosed environment to reduce moisture and energy requirements using condensation hood or and recirculation. With the efficient dishwasher, we can reduce up to 50% the energy demand using heat recovery from wastewater. An improved insulated housing reduces heat losses because the detergent solution in the machine is continuously kept at the high temperature. Pre-rinse reduces wash time and detergent consumption, and use of low-flow pre-rinse spray valves. Refrigerators are another important element to consider because they are running 24 hours per day and mainly the whole year. So through structural measures such as improved insulation panel and airtight construction method, the useful energy demand of the cold stores can be reduced up to 70%.
In summary, we've reviewed the three major elements impacting the energy consumption of commercial kitchens. First and foremost, the kitchen ventilation. We need to right size that kitchen ventilation, and that can be done first through careful planning, then through the use of high efficiency technology, including the demand control ventilation. Second, a big focus on kitchen equipment. So there's a need for highly efficient equipment, and that can be achieved through careful specification. Finally, the domestic hot water component. We need to reduce as much as we can the domestic hot water demand, and that can be done through the use of waste heat to deliver domestic hot water preheating whenever and wherever that waste heat is available. And to bring it back to the design team, this level of optimization in the design, I want to highlight that it cannot be achieved without a high client engagement in the process, as well as an integrated design approach with all consultants. And that includes the kitchen consultant as well as the kitchen staff, in addition to all the more standard disciplines. And this interaction and coordination and high level of communication will lead to a deep understanding of the various kitchen usage and profiles, which is at the core of designing these high performance commercial kitchens. For further reading, we've gathered a list of Pacipedia articles which start diving in a bit more depth on different aspects of the commercial kitchens and their energy consumption. So please feel free to check it out. So thank you very much on behalf of Roberto and I, and we look forward to answering your questions during the Q&A. Thank you very much.
Wow, Maureen and Roberto, this was such a session. So informational. I mean, such a challenge to try to tackle this kind of problem. I mean, making a passive house is hard, but making a passive house building with a commercial kitchen, it's like triple hard, or it's unmeasurably hard. So I hear you've been working 2 years on this problem, and thank you for sharing all this hard-earned knowledge with us. I mean, commercial kitchens are kind of hell on earth. High internal heat gains in there, full of people. Indoor air pollution is high, but they're used at kind of set intervals for short time, right? So that also exasperates the problem. And is the equipment available, that can help you achieve passive house standard? That's also another challenge. And what are our PHPP challenges to try to make this work for the standard? So thank you for sharing this with us. I'll now try to go through some questions that were posted online during the session. You have answered some of them already, but for the rest of the audience, I'll just read through them and ask you again to try to elaborate on that. There was a question about the arrangement of hoods. This was at the beginning of the session. You stated that there's a large range of efficiencies that you have observed. And the question was, how did you measure that? How did you arrive at that conclusion?
Yeah, this is has been made by the manufacturers. So it's mainly the manufacturers that are bringing and are pushing these, we can say, these researches about range hood. So this is results of CFD analysis and also we can say real world test. So this is a mix of these two aspects.
Were those CFD analysis done by you guys or by the manufacturers?
No. The manufacturers or also other institutes like for research of food or kitchen research. About kitchens. So yeah, it's a mix of information that we collect, and we know that there is this influence in this range, in this space. And so there is a strictly relation between the diameter of the duct and the 100% of, we can say, efficacy area for suction. So we can say the induction hood, it's at the end, it's really, really, really important for the ventilation, for the quality of the ventilation, and to reduce the heat losses due to the ventilation system.
Right. Thank you for that. Maybe a follow-up from my own point of view. I think I've seen in one of your schematics that the makeup air that is coming for the exhaust hoods is coming through the hood. And is it also tempered? You mentioned tempering this makeup air from the outside. Does this technology already exist? Maybe Marie can answer.
For the UVIC project, we don't have any, makeup air that is not tempered, right? To make sure we're maintaining comfort with the way everything is set up. But we have found, on a separate project that we're working on, the one for the University of Toronto, again, to trying to avoid paying for that preheating, right? Because makeup air in itself is not what costs us energy. Is like to heat the makeup air that you need to make up for the kitchen exhaust. We found a way to, how to say that in English, like just divert the minimum we need for the hoods, knowing that if the air is supplied directly to the hoods and extracting straight again, that portion does not need to be preheated.
Right.
So we've managed to have that kind of diversion, and that little part we're not paying for the second project on the University of Toronto.
Right. Yeah, that's what I noticed, that makeup air was coming directly into the hood, and it's being mixed with the exhaust air that's coming right out. I mean, this is kind of a holy grail for passive house kitchen hood exhausts in residential as well, right? If you have come close to a solution to that, would be through the research in commercial kitchens, this would be awesome for the rest of the passive house community. So there was another question asked about cascade ventilation. So you mentioned that ventilating directly out is not very efficient, that there are lots of losses, but you've come up with another approach. So maybe you can elaborate on that a little bit.
Yeah, for sure. So cascade ventilation is the idea of, if you have two spaces, rather than supplying and extracting a total amount of air to each room, right, which costs you 2 times that total amount. You're trying to supply to one of them and exhaust from the other one, so that the total amount of flow rate is actually half of it, right, as a, qualitative way. So in our case, through the commercial kitchen, so you always have that commercial kitchen part where you're cooking and a dining nearby. So you want to exhaust from the kitchen space, you want to supply from the dining hall. And so rather than, if you focus on the kitchen needs a certain amount of exhaust, right? Because of the cooking requirements, rather than for you to pay for the 100% of the makeup air, which is what costs you money, right? To preheat that makeup air, to balance the space that you're having right here, you're actually doing a little bit from outside, which you have to preheat and cost you something, energy-wise. But the other part of it, you're actually transferring that fresh air from the dining hall, which is not considered yet, a very dirty air by the time it comes to the kitchen and gets exhausted. So overall, when you zoom back and look at your, non-residential portion of the building as a whole, you've managed to reduce the overall amount of flow rate that is happening in your building. And that overall reduction is directly translated to a lower amount of air that you have to preheat, that costs energy and, has an impact onto your space heating demand.
Right, you're using preheated air already from somewhere else.
Yeah.
To ventilate the kitchen, right? So perfect.
And also in general, the supply air in the kitchen is not counted at 20 degrees. You can reduce the temperature, so until 17 degrees Celsius, it's still acceptable. So you have also a bonus in the heat recovery efficiency for that.
Perfect. Thank you for that. All right, so the questions started pouring in right now. So it seems like we have woken up the audience. So another question about CFD and the placement of the range hood, and how does that affect efficiency? Anything that you can shed a light in terms of physics or fluid dynamics that is happening there?
Yeah. I mean,
in few words.
Exactly. It's as I said before, it's a mix of real world test to see the behavior of the smokes and the fumes, and the CA and CFD calculation and analysis made for also to get, we can say, a correspondence on the real world and the calculation itself. Now the exactly physical processes inside these range hoods, in few words is also a bit harder to explain, but yes, as I said before, there is this area that is, we can say, the distance I'm going with the fumes from the extract point, the lower is the efficacy. For this, in one of the slide, there is an improvement that you can get, reducing the high, so the distance between the cooktop and the range hood itself. So reducing this distance, you can improve the efficiency, keeping the same, we can say, airflow rate, but you are improving the efficiency. So now about the CFD calculation or physical fluidodynamic analysis. Now, it's also a bit hard, but keep in mind, I think the most important point is the higher is the distance between these two objects. So cooktop, extract hood, the lower is the efficiency. So the higher should be the airflow rate to catch all these fumes.
Right.
Yes. So actually, Roberto, I would even say it the other way, where we know that from an energy standpoint, it's your exhaust flow rate that hurts you, right? Whatever exhaust you need to make your kitchen work, you have to match it with the makeup air. The makeup air you have to preheat, and that costs that is using your space heating demand budget that you'd rather use on windows and other things. So knowing the kitchen is set as it is, right? Like there's a certain amount of meals and services that you're trying to get out of that. Our goal is to make sure we can deliver this service with the lowest amount of exhaust flow rates, right? And so as you can imagine, even without like CFD calculations or trying to make it slightly more visible to everybody, when you're cooking something, the air goes a little bit everywhere, right? It's not going to behave really, really well and just go straight up to the range hood. It's going to try to escape. So the more enclosed you are by walls, by rail guards, by even air curtains, and the closer you are to the point where you're cooking, the more of that plume you're going to start to grab, right? So by using all of that, this is how you can still deliver the same amount of services, but you actually need less exhaust to deliver what you're after.
Great, thank you. Great insights. Okay, so questions are coming in. All right, so there's a question about the HRV, the particular one that you have chosen for this project. What is the brand, model, and maybe if you can share the link to it.
Yeah. So a bit of a downer on that one. So we had a quick slide on the HRV, and we went through a lot of trouble because, as I said in the presentation, we started with one in the middle of a project like that has been more than 3 years of design, literally from schematic design to construction drawings. So the unit got discontinued in the middle of it. So we started looking at bespoke HRVs built in somebody's backyard. We went to Europe to trying to find them, but these units didn't have like CSA approvals, or they weren't big enough. Like we needed to get like 10 of them, and there was no space anymore in our kitchen that was already designed. So more or less, at the end of the day on this project, what we're working with is simply a kind of ecologizer unit, so a unit that takes away the grease and the pollution, which is then coupled by a very simple runaround loop. And it is the runaround loop that is simply giving us that heat heat recovery, right, between the two airstreams. So not quite the whole, fireworks that everybody was expecting, but this is the best we could do on this project, because of course, as Roberto mentioned, the whole grease aspects and fire safety is a big one for commercial kitchens, right? As much as us, passive house designers, we would love to have the most, the highest heat recovery efficiency we would want on these units, we will never come close to the one we typically use in residential buildings because of that grease and fire safety aspect. So you have to know that when you're starting an archetype, like a building with that typology in, the heat recovery you're going to have associated to the kitchen is going to be in the magnitude of, 20-25+% lower than what you would normally get. Right.
Well, thank you for that. So when you say runaround loop, so is this some kind of a custom heat exchanger of pipes running next to each other or something?
And I wouldn't even say custom. It's like a kind of the most basic type of heat exchange where you've got two airstreams and you simply have that glycol loop just moving between the two and just transferring heat.
All right, so it's air to fluid back to air.
Like a runaround coil.
Yeah.
I see. Gotcha. All right, so the question that it's related to this one, maybe it can help you. I'm not sure, but Tad says that he has heard that in the Netherlands, at the location near the Zender manufacturing plant, there is a hotel with a commercial kitchen with HRV by Zender. So did you look at Zender in your process?
Yes. Okay. So that's a really good question, Ted. I had heard about this, but we didn't even talk to Zender because this is UVEC and the size is 9,000 meals a day. And I don't think we have the space for 50 Zenders. Like, I'm guessing it would be somewhere like that. That was the difficulty as well, right? Like when you look at the passive house market, you have more options towards single family all the way to, multi-residential, but we don't do yet the big and bold, right? We don't have that many certified units that are huge and able to tackle whole office towers or things like that. So purely on that aspects, we've been talking to people that we normally don't talk to, right? Because Roberto actually and his colleagues at PHI gave us a lot of tips about like all the heat recovery units that were used in Europe in passive house commercial kitchens, but most of them were like close to a factor 5 to 10 smaller than what we were after in this case.
Right.
Like we are getting out upwards of 9,000 meals a day in that kitchen. Like that gives you the size of it, the sheer amount of cooking that is happening in there and the associated flow rate when everything is in full mode.
Great. Thank you, Marie.
And sorry, can I add? And the same happened for the other appliances. So griddles, oven, everything in a residential market has a label, like, I don't know, Energy Start or a quality label or energy label. But in this field, so far, it's almost, we can say, empty. So for this, we have followed the two approaches, qualitative approach and quantitative approach. Because sometimes you don't have the data from the manufacturers for the quantitative approach. So you cannot quantify the energy. So you have to follow the qualitative approach. So choosing the appliances following characteristics like insulation, low emissivity, coatings, triple glazing, and stuff like that. That in a passive house, and the envelope is always the envelope. The oven needs triple glazing, low emissivity coating. So it's like an envelope of a normal building, and yes. So this is another point that so far the market is quite, we can say, empty of data for this kind of buildings.
Yes, you're definitely trailblazers in this respect. So we appreciate your effort here and sharing it with us.
Sorry, and the last thing, and also few words, because I would like to also to say thank you to my colleagues Oliver K. and Christine Brownlich, because they are we can say the main researcher of our institute about this commercial kitchen. So I think it's good also say their name and say thank you to them for the great job they have done all along this project.
Yeah.
Yes.
I have to say I'll just add a little bit to that, but this was a serious team effort. I know we normally say you design your building, then you send it to the certifier, but I think this was almost like a joint effort of design for like several years, because we were doing a lot on the ground, and our design team, like the involvement that we had, like you can hear right from the ventilation, the equipment, like it was like mastery and going to a whole new planet with the mechanical engineer, the kitchen consultants, the architects, as well as the kitchen staff and the university themselves, right? So you need that team to be really deeply involved into every single thing that we do, because everything is linked to each other. And then we were backed up heavily by the whole Passive House Institute team. Like without, Roberto and his colleagues and all of us together, I don't think we would be here presenting this today or being that successful. So I have to say, again, when you're working with a new typology, just make sure you get as many brains around the tables, because it's needed.
Absolutely. You were fortunate that you had those resources and those people willing to help you. And thanks for the plug for the articles that are already on the Passipedia about commercial kitchens. So those that are interested can go there and read the latest research on this. So there are a few more questions. We have 10 minutes left. So there was a question from Christina saying, trying to see how did you make a decision between gas and electric, since using electricity for heating, let's say for the resistance heat, has the same efficiency as gas. Did you first, maybe I'm adding to this question, did you go to induction heating at all? Are there, is there equipment that for commercial kitchens with induction? But she was asking, is the reason for switching from gas to electric to reduce the amount of effluents or the exhaust gases that are produced by burning gas, which would maybe help you in, reducing your ventilation loads. So one question from Christina and one add-on from me.
Okay. No, and so that's a really good question. And I think the switch from gas to electricity and induction is actually tackling 3 different points at the same time. So first of all, in terms of energy requirements, right? Because you saw that we were doing like an equipment by equipment energy calculation. The energy required for these equipments to operate, on average, the electricity version will save some energy compared to the gas one. We're not talking again, I don't have the exact calcs open in front of me, but I think from memory, we're not talking about a 50-60% cut, but it's still a cut. On average, all the electricity-based equipment will use less. So that is definitely helpful to start with. But I think more importantly is that the electricity and induction equipment will have a much larger impact on the reduction of exhaust flow rate, which is really our primary culprit and the thing that impact our space heating demand the most. And finally, and more importantly on this particular project, is that the University of Victoria decided on Passive House as a, climate mitigation and adaptation solution. And for them, Passive House was the solution to meeting their campus greenhouse gas emission reduction targets, right? They're putting more and more students onto the campus. They're even adding more residences, right? So not even just the teaching part, but people living on campus. And while adding all these students, they have already agreed to a significant cut in yearly greenhouse gas emission reduction. And so just to give you, I'm going to put this in context, right? Us as Passive House designers, we are used to, of course we talk about final energy, we talk about, EUIs, right? But I think most of us are starting to talk through that PR value, right? Where we can compare buildings. The default criteria is 60 kilowatt hour per square meter per year. Sorry, in metrics, somebody can translate that to imperial in the chat. 60, and you're going to move to 70, 80, 90 based on density for potential, more densely occupied buildings. The PR of the non-residential podium, so I'm not even talking about the kitchen, I'm talking about the 2 stories of non-residential space, has increased from 60 to 660 kilowatt hour per square meter per year, with the best kitchens we've ever designed, as far as I'm concerned. And that typical kitchens would take this, higher, a factor 4 or 5. So when you can make a dent into the operation and the greenhouse gas emissions of your kitchen, the impact that it has when you zoom back, look at your number of meals and your daily production, because that kitchen is in use 365 days a year. This just tackles so much of that issue they're facing, right, in terms of delivering their greenhouse gas emission reduction.
Excellent. Thank you. Thank you so much for these insights and the answers.
And also there is a point related to the thermal comfort, that with the gas, you cannot reduce we can say the internal heat gains produced by gas or fire appliances. Meanwhile, using electricity, you can use appliances with the low emissivity coating. So you can reduce at the same time with the low emissivity coating the internal heat gains, so the heat release inside the ambient, the space. And at the same time, with low emissivity coating, you can also reduce the energy needed to keep at a certain temperature we can say the plate or the griddles or anything inside. I mean, everything inside the kitchen.
Right. So multiple benefits there.
Yeah.
So another question from David. So is this kitchen in use? Has this been completed or?
Yeah, okay, so that's a very good question too. It's a very, very large building. So it is currently in construction. We're passing level 2, but this is a 8-9 story building under construction. So my understanding is that we should be in use at, best case, September 2022, if not, early 2023. Because it comes with the student residence and we have to do the whole thing before we open up. So that's the only, downside of working on a really large project. They take quite a while to actually materialize. But what I can say is that Roberto and I have been working really hard on that one. And I'm pleased to say that the Passive House Institute has given the, letter of assurance for pre-certification. So we know that on paper, this building is certifiable. Now we just need to build it as we said we would. So
right.
That's just another, small thing to get through.
Just small thing to get through, right? So the question was related actually to monitoring and comparing the actual to the modeled use, but that remains to be seen.
Well, let's be fair. I think most of the project we're working on, we are trying to ask for as much monitoring as we can, because it's definitely an area where we don't have enough. So no matter what, we are going to try to monitor everything we work on, just to start informing a little bit better, how the actual performance relates to all the calculations and, qualitative decisions that we've made, right?
Right approach. Okay, so I'll ask another question from Tad. It's a very popular question, I guess. The question was, have you found a domestic hot water heater for commercial kitchens which is integrated to cool walk-in refrigerators or freezers? I don't know if this type of equipment exists.
So again, I'm not going to say it doesn't. It might on a smaller scale. But again, with the size of what we're dealing with, we did exactly that, right? All our all our walk-in freezers and coolers are connected to that central compressor loop where the heat is rejected, and that heat is used to preheat the domestic hot water that we are using on site. So we are using that exact same process, but at the moment on that scale, made as a piecemeal approach, right, by the mechanical engineer, which who is gathering all the right pieces and assembling them all in the right order to get us to where we want to go, right? We don't yet have a big box where you just dump it there and be like, yeah, it does everything you want right now. I hope that we're starting to see some of that exist on at least a smaller scale. But for now, we have to say, so the mechanical engineer on this project was integral. And so again, they've done an amazing job at gathering all the moving pieces and making sure that all the systems were rightly set up so that we could use as much of that waste heat as was available to reduce our overall, energy consumption.
Right. If such equipment existed, it would make it too easy for you guys. And we didn't want that.
Right.
All right. So another question. Is the kitchen or prep food storage and dining areas separate from the student residence towers? And any thought on, using any waste heat from the kitchen in the residential areas? I mean, has any thought been given to that?
So The residential portion is above the commercial kitchen. So we have 2-story podium with a 2-story dining hall and a 1-story kitchen and additional, laundry and communal facilities. And then the residential tower is above that portion for building number 1. Building number 2 is the same with teaching spaces in the podium and residential above. This is the way the building is set up. And in terms of, moving heat to preheat other spaces, we know that moving that heat is not the easiest thing to do. So the way we are reusing that heat is back through that runaround coil, right? Because everything that we're extracting from the kitchen goes through that runaround coil to preheat the incoming makeup air to the kitchen, right? Because for the portion that goes to the kitchen staff, we are not giving them just cold makeup air, right? We have to preheat. Even if we're not preheating to 20 degrees, we're trying to preheat to 16, 17 degrees, so that with the internal heat gains from the kitchen, they're still around 20 and at a, internal environment that is adequate, right? Like trying to avoid them being too hot. So this is how we're reusing in a more efficient way. And then we do have much better, higher efficiency ERVs being used on the residential portion, right? So this is where we're working with large Swigon units.
Excellent, thank you. I think we're right on time. I believe we can talk about this all day long. Very interested in all your progress and can't wait for this student building in the kitchen to be put in use so we can see how it actually works. And I want to thank you again for your hard work in the past 2 years and for your generosity in sharing this with us during this conference. And I wish you all the success for the future and see you again at the next conference. Thank you.
Thanks for having us, Vlad. Thank you again.
Thank you very much. Thank you to all.